again. In this topic, we're learning about curve sketching. I'm going to break up this topic into 5 separate videos, where in each video I will show an example of sketching a curve using this process that I have listed here. So here's a general idea of the steps you can take to produce a curve, a sketch of a curve, using algebra and now what we've learned in calculus. Now from algebra, we should know things like, what's the domain of the function? Are there vertical asymptotes? Intercepts, if they're relatively easy to find, remember that to find intercepts, we either set the input to 0, right? So we evaluate f of 0 and solve f of x equals 0. That will give us the intercepts of the function. And then we can run a symmetry test to see if the function is odd or even. Now, that's not necessary, but it can be useful because if you do notice symmetry to the curve, then really you only have to do half the work and then just use the appropriate symmetry. All right, then the calculus. We analyze with the first derivative to find find the critical numbers and intervals of increase or decrease, and find the relative extrema. We analyze with the second derivative to find intervals of concavity and the inflection points, if possible. We can analyze the end behavior of the curve by taking the limits of the function as x approaches negative infinity or positive infinity. Then we can break up the entire number line, the domain, and think of a number line and break it up into subintervals based on the critical numbers and the values we have from the analyzing with the second derivative. And we can take each subinterval and then use the first and second derivative information to say what will the curve look like on that subinterval. And then we're going to take all that previous information and draw a sketch of the curve. So let's see an example. Let's consider the function x squared divided by x squared plus 9. So the first thing we know from algebra is, well, this is a rational function. We should be concerned if the denominator could ever equal 0. We have x squared plus 9 in the denominator. That can never equal 0. So I know that the domain is all real numbers. We can easily find the intercept. Notice that f of 0 equals 0. And so I know the curve passes through the point 0, 0. And that's in fact the only intercept of the curve. Because the numerator can never equal 0 except at x equals 0. This curve will have no vertical asymptote since the denominator can never equal 0. We might also notice that the function is even. F of negative x is then negative x squared over negative x squared plus 9, which is x squared over x squared plus 9. And so then that's equal to f of x, so even. So that means I'm expecting to see symmetry about the y-axis. So that's a good thing to remember, that if we don't have that symmetry, it means I've done something wrong. All right, let's do some calculus now. So let's find the first derivative, f prime of x. That would be 2x by x squared plus 9 minus x squared by 2x over x squared plus 9 squared. Okay, and we simplify this, and this ends up being 18x over x squared plus 9 squared. And so we look at this, the denominator can still never equal 0. The numerator can equal 0 if x equals 0, so I have a critical number at x equals 0. Breaking up my number line at 0 and testing into the first derivative, we we see that the sign will change only at x equals 0. And let's see, if we're to the left of 0, 18 times a number less than 0 would be negative. 18 times a number that is greater than 0 would be positive. So then the function f is decreasing on negative infinity to 0, increasing on 0 to infinity. And further, we know that there's going to be a relative minimum, and actually it's got to be, it turns out to be absolute minimum, because if we know that the function is strictly decreasing then increasing, then it must be a minimum, an absolute minimum. But we know that there's a minimum when x is 0, and we know that if x is 0, the output is 0. So it turns out that there's a minimum at 0, 0. We know that that's the intercept of the curve. Let's calculate a second derivative to talk about the concavity. So the second derivative of the function would be, let's see, we'd have 18 by x squared plus 9 squared minus 18x by 2 by x squared plus 9 to the first by 2x. And that's all divided by x squared plus 9 square, so 18x squared plus 9 to the fourth. And you should be able to do these steps, but if after you simplify this, removing any common factors, I did this on the side. Let's see, I get that this simplifies as 162 minus 54x squared over x squared plus 9 cubed. Now again, the denominator cannot equal 0, but the numerator can equal 0. If we find, we solve 162 minus 54x squared and set that equal to 0, then x squared equals 3, which then means that x is positive or negative square root of 3. So then we have two important numbers for the second derivative at negative root 3 and at positive root 3. Negative root 3, positive root 3. And if we test this into the second derivative, let's take a number, how about, well, let's start at 0, start in the middle. If x is 0, then 162 minus 0 is positive. We know the denominator is going to be positive, so the second derivative is positive here. And let's pick a number greater than square root of 3. How about we pick 4? 4 squared is 16. 54 times 16 is larger than 162, so this has got to be negative. And the same thing happens over here on to the left. So what we now know is that f is concave down on negative infinity to negative root 3, concave up on negative root 3 to root 3, and then concave down again on root 3 to infinity. And then we have inflection points, since the concavity changes at positive or negative root 3, and by noticing the symmetry of the curve, we then can evaluate that. We know that the inflection points if we let x equal either negative root 3 or root 3, then x squared would be 3. So we would have the inflection points at positive or negative square root 3, and then we would have 3 over 3 plus 9, that's 3 over 12, that's 1/4. So I'll write the decimal number 0.25. Now, what's next? End behavior. What happens if we take the limits at positive or negative infinity for the function? so let's take the limit as x approaches infinity of x squared over x squared plus 9. And we could either use algebra or L'Hopital's rule here. What I'll do is I'll just use the algebraic technique. I'll multiply by 1 over x squared in the denominator, in numerator and denominator, and this becomes the limit as x approaches infinity of 1 over 1 plus 9 over x squared. And so then that's 1 over 1 plus 0, taking the limit as x approaches infinity, and so then that's 1. So, and it ends up that we get the same thing if we substitute a negative infinity, right? If we take the limit as x approaches negative infinity. So that means we have a horizontal asymptote at y equals 1. On both sides, right? As we move either far to the left or far to the right. Alright, so now let's take all that information that we've learned and think about the shape of the curve in each interval. We had only really 3 important numbers, at 0 and at plus or minus root 3. So if we take all that information together, here's 0, here's negative root 3, and here's positive root 3. And let's think of the first derivative and the second derivative. Alright, let's look back a moment. So it was decreasing up to 0 and then increasing after 0. So the first derivative said we were decreasing and increasing. The second derivative said we were concave down, then concave up between negative root 3 and root 3, and then concave down again. So if we think about the shape of the curve, right, what is the shape over each of these intervals? Decreasing and concave down over the first interval. Decreasing and concave up over the second interval. Increasing and then concave up. Increasing and concave down. So there's the general shape of the curve over each interval. Now let's fill in the details. What are the important points? I've got a minimum at 0, 0. I've got inflection points at y equals 0.25. And then I've got a horizontal asymptote at y equals 1. So for my scale, I'll make 4 marks be 1. I'll make this be 1. And I'm going to draw in, I'll draw in blue so we can see that better against the background. So I know I've got a horizontal asymptote at y equals 1 far to the left and far to the right. And let's see, I'll make, where are my important values? Well, I know I'll pass through the origin at 0, 0. And then my inflection points are at negative, plus or minus root 3 and 0.25. So let's make this negative 1. So here's negative 2. So here's 1 and here's 2. And you know, the scale you use, that's up to you. But I've got important points, inflection points at plus or minus root 3. The square root of 3 is about 1.732. So at negative 1.732, so about here, 1.5, 1.7, the inflection point is at 0.25. So there's my inflection point, and then symmetry, I should have an inflection point in about the same place on the other side. The curve is asymptotic to y equals 1, decreasing and concave down. Then changes to decreasing and concave up. Is increasing and concave up, increasing and concave down and asymptotic. And there's a rough sketch of the curve f of x is x squared over x squared plus 9. So this is a model for the process that I expect you to be able to use. And I'm going to show a few other examples of this process in the remaining videos for this topic.